All right, so today what I wanted to do was part of the free response you see right here, which is an electrochem one, which would usually be pretty easy for you guys, seeing as we just learned it. But remember, like I said, that's not going to be on the exam. All right, that falls in the out of the content. So I really am targeting review to stuff that you might see. But there is a part of this question down here that you could see, all right, about solubility. All right, so we're zeroing in right here, all right, where it says the student adds some NaCl to the half cell that contains Cu plus and Cu plus 2 and a precipitate forms. It says, based on the information in the following table, determine the identity of the precipitate, and it says justify your answer with a calculation. So they're giving you the solubility and they're giving you the KSP, but not of both. They're giving you one of each. All right, so the first thing it says is, based on the info, who is the precipitate, and justify it with a calculation. So when we're trying to predict precipitates, remember, one way we can do it is a QK comparison, right? That's probably the most popular way, but this setup isn't leading us toward that. If they give us KSP, you know how soluble it is. Now, if we had both substances KSPs, you could compare them, but there's only a special circumstance where you can compare KSPs to see who is going to precipitate. Anybody remember when that is? It's kind of a tricky one. When are we allowed to compare just KSPs if we have them?
When they break up into the same amount of pieces.
Correct. All right, so if they break up into the same number of pieces, I can compare KSPs. If they don't, remember, we have to get both of their X values and then compare those. All right, now they gave us the CuCl2's X, but they didn't give us this guy's. So what you have to decide is, who is it more worthwhile to get? This guy's KSP to compare it, or this guy's solubility, which is X, to compare it. And the reason I'm going to say we want to get the solubility is because CuCl breaks up into 2 pieces, and CuCl2 breaks up into 3 pieces, Cu plus 2 and 2 Cl negatives. So getting the KSP of this guy really doesn't help us. So we have to get CuCl's X value. All right, so remember, solubility is always the solid breaking up, KSP, into the ions. All right, looking at an ice table, but dash, 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 because the CuCl is a solid. 0, 0 here. X, X, right? X, X again. Next step, we plug it into the K expression. This is a KSP expression. It's going to be equal to X squared. We know the KSP. It's 1.7 times 10 to the negative 7. All right, so we got to solve this guy for X. So we're taking the square root of that. So second square root of the 1.7 e negative 7. All right, so if I do that, I get 4.0 times 10 to the negative 4th. All right, there's my X value. So we get to compare this guy to the 5.2 of the other guy. Who's bigger?
5.2.
5.2, which means CuCl is more, or CuCl2 is more soluble than the CuCl. So who will the precipitate be based on this being 5.2 and this being to the negative 4th?
CuCl.
Good, right? The smaller one is less soluble, right? And less soluble means you'll be the precipitate. All right, so you guys would want to say for E, CuCl with that supporting math work and saying that the 4.0 is less than the 5.2. Then it says, what's the net ionic equation for the formation of the precipitate? All right, so my net ionic equation for forming the precipitate is just going to be the reverse. Okay? Cu plus the Cl negative going to the CuCl. Right? So you have to just be careful on the reading there. You're forming the precipitate, which means we had to put the precipitate on the right side. All right, questions on that part? Okay. All right, so rounding out this practice test, all we have left is the one that we ran out of time on yesterday, which was number 7. Okay, so if we take a look, they're describing some solutions to us. We've got 100 milliliters of 0.10 molar NaOH mixed with 100 milliliters of 0.10 molar HBr. All right, so we've got one set where we've got NaOH with HBr. All right, so that's solution X. All right, solution Y, all right, we've got NaBr with HBr. And I'm not even listing like amounts and concentrations because look, it's 100 mil of the same molarity of all of them. So it's obviously who the substance is that's controlling some stuff. And then the last one, we've got HC2, H3, O2 going to Na, C2, H3, O2. All right, so there's my 3 pairs. It says student prepares those solutions. They give you relevant Kas if you need them, right, for the HC2H3O2, and they're telling you the HBRs is really large. And it says, using the information above, rank them in order of increasing pH. Explain your reasoning. So if we need to figure out stuff about pH, what are they really asking us?
The
if it's acidic or base.
Exactly. We got to figure out like what the solution is going to be. All right, so let's go through and see if we can remember some stuff. All right, Abby, is your computer still working?
Yeah, I'm here.
All right, so NaOH, talk to me. What kind of base, acid, salt? What are we looking at?
It's a base.
What kind?
No, it's a salt.
No, you're right.
Oh, okay,
It's a base, but is it weak or strong?
It's a strong base.
It's on our list, right? So NaOH is a strong base. All right, Alexandra, you with us?
Yeah,
All right, how about HBr? What is that?
it's a strong base.
Close, strong.
I meant strong acid.
Yeah, you got it. All right, so there's our pairing there. All right, how about Angel? All right, how about NaBr? What do you think you have?
That's the neutral salt.
All
And
right,
then
good. So, right, Angel took it all. She said she knew it was a salt. She wanted to figure out what kind. So she did the breakdown thing, right? NaOH is a strong, which says neutral. HBr is a strong, which says neutral. So she knows, hey, I've got a neutral salt here. All right. Camille, how about HBr? What are we thinking?
Strong acid.
Good. All right, moving on down the list. Carmen, how about HC2H3O2? What's that?
Weak acid.
Agreed. Right, not on our list of 6, but it starts with an H. All right, and Elena, how about NaC2H3O2?
That would be a acidic salt.
Yeah, so let's break this guy down, right? The NaOH says neutral. The back half tells me neutral or basic, though, and it
Then
means
a
it's going to be a
basic
basic salt. All right, so no big deal. Okay, so they want lowest pH to highest pH. So take a look. If I put a strong base with a strong acid, all right, Ethan, what do you think that's going to do if I mix a strong with a strong?
Neutral.
Bingo. So there's a neutral. All right, how about if I take a neutral salt with a strong acid, John?
I'm sorry.
If I did a neutral salt paired with a strong acid, what's the overall mixture going to be?
It's going to be a low pH. I mean, yeah.
Yeah, you're right. Low pH. It's going to be real acidic. All right. And if I did a weak acid with a basic salt, what are we going to have, Sydney?
It's gonna be basic.
Starting with a weak acid. Right? So it's a weak acid. And really, don't forget, this is a weak acid with its conjugate. What is this really?
Oh, it's a buffer.
It's a buffer. And what kind of buffer is it going to be?
An acidic.
An acidic buffer, because it's right. It's always based off the weak, right? All right. So we've got an acidic buffer here. Okay. So now you guys know what you're looking at, right? The lowest pH has got to be the one with the strong acid in it, right? So I'm looking at what's the NaBr? So that's Y is the lowest pH. It's going to be less than the acidic buffer, which is Z. And the highest pH is going to be the neutral up above. So that's X. So you're looking at Y to Z to X. All right. So we got letter A. B says, does the pH of solution Y, and it's probably worth my time to come up here and label these guys. All right. So this is X, this is Y, this is Z. Okay. All right. So does the pH of solution Y, this guy, increase, decrease, or stay the same when we dump 100 mils of water in? All right. So Mia, if I dump water into this substance, right, which was pretty much a strong acid, if I pour just water into that strong acid, what do you think it's going to do to its pH?
Is it going to make it more basic?
I like it. I wouldn't say more basic. I would just say less acidic, but you're right.
Okay.
Because what are you doing to the acid when you add water to it?
Are you neutralizing it?
You're not neutralizing it. You're diluting it. Yeah, like if I added a base in, I'd be neutralizing. But I'm diluting it, and diluting it's going to make it not as potent in pH as well. All right, so for B, you guys want to say pH decreases because adding water decreases the concentration of H3O plus. All right, so now into C, it says the student adds 0.0010 moles of NaOH to solution Y. So we add NaOH to solution Y and 0.100 NaOH to solution Z. So we add NaOH to both these bottom two here. And it wants to know, assume the volume doesn't change. The pH of solution Y, this guy, changed a lot more than this guy. All right, explain the observation. All right, so Jan, what are you thinking? Why is it this guy's pH changed more and this guy's pH changed less when we added base to it?
Because the stronger one has more H3O plus that the base, the OH in the base will go to attract more, and the weak acid don't have a lot, so it won't be as attracted to, the base won't be attracted to the weak acid.
Base 1, base 2. So the only trouble is the base will go after both. So the strong base will go after HBr and HC2H3O2 the same. Right? So don't think of it that way. Anybody else have thoughts on that?
Z is a buffer, so it's going to fight pH change.
There it is, right? That's exactly what buffers do. Right? Because Z is a buffer, you've got weak with conjugate. When I dump the NaOH in here, right, it gobbles up the OHs, keeping the C2H3O2s, right? That's what buffers do, right? They keep the OH from going after H3O pluses. All right, so you want to just say for C, solution Z is a buffer, and buffers resist pH change. Questions on that one, which would round out that practice test. Any topics there you guys weren't sure about? Okay. All right, so I wanted to do two last short ones from a different test. All right, so we're going to take a look at this one here, which is numbers 4 and 5 I want to take a peek at. So, okay, so here's number 4. Zoom in a bit for you. Get a clean screen there. All right, so they give you the reaction there at the top. You've got CaCO3 going to CaO and CO2. It says when we heat the calcium carbonate, it decomposes. In a study of the decomp of calcium carbonate, student adds 50 grams of the CaCO3 to a 1 liter container. The student sealed the container, pumped out all the gases, and then heated it in the oven. As the container was heated, the pressure of the CO2 was measured over time. Here's your data. So we've got a pressure of the CO2 that we're creating over time, increases, levels off. Student repeats the experiment, but this time he used 100 grams instead of 50. In this experiment, the final pressure was 1.04, which was the same as the final pressure above. All right, so the first question wants the number of moles of CO2 present in the container, right, after 20 minutes. All right, so I want to get moles of CO2 for letter A. Abby, any thoughts on how we can get moles of CO2 after the 20 minutes?
No, I don't know.
All right, so what's your graph tell you? So you know 20 minutes. What do you know at 20 minutes?
The pressure.
The pressure. So what's our pressure?
At 20 minutes?
Uh-huh.
1 atmosphere.
Close. 1.04.
4.
Right, and I knew that because it was buried in here, right? We knew that graph got just above the 1. All right, so I know a pressure, right? I know the size of the container, and I know the temp. Any thoughts on how we can get moles given that?
PVNRT.
There we go, right? So PVNRT is what we're going to do. So you do PV equals NRT, which means N is equal to PV over RT. And then we plug in. Pressure's got to be in atmospheres, so it's 1.04. We're good. Volume's got to be in liters. It was 1 liter, so we're okay. R is your constant, 0.0821. And the temp they even had in Kelvin for us. So they did a lot of the conversion work for us. All right, so we punch that into our calculator. So I'm looking at 1.04 divided by 0.0821 divided by 1100. All right, so I get 0.0115. Moles of CO2. Oh, and some of you may say, well, like, why can't I just take the 100 grams and convert it into moles. Right? We have to realize if we did that, we're assuming that all of the CaCO3 decomposed, right? And we don't know that that happened. In fact, we probably think it didn't, because whenever I had 50 grams, I got 1.04. And whenever I have 100 grams, I got 1.04. Right? So if we were reacting at all, my pressure should have been different between those two. So it means I didn't even react all of the 50. All right, so that's why I can't do it that way. That's why I'm doing pressure and the PVNRT. All right, so into question B. All right, B says, the student claimed that the final pressure in each container became constant because all the CaCO3 decomposed based on the experiment. Oh, sorry, I already answered that question. Okay, so it says, does it agree with that claim? So for B, you want to say no. If all the CaCO3 decomposed in both, here's the part I can ask you guys, though. If all the 50 decomposed and all of the 100 decomposed, what should the pressure have been the second time?
2.08.
How'd you get it?
Double.
Exactly. If I used double the sample size, I should have gotten double the gas, which would have made me get double the pressure. And that didn't happen. That's how we know that. So finishing out B, the student claimed the final pressure. You would say no. The pressure was the same for both, which means not all the CaCO3 reacted. All right, so into question C. All right, C says, after 20 minutes, we injected some CO2 and we initially raised the pressure up to 1.5 atm. Would the final pressure inside the container be less than, greater than, or equal to 1.04? Explain your reasoning. All right, Alexandra, what do you think? And this is a tricky one, so no worries if you're stuck.
Would it be less than?
Tell me why you're thinking that.
I honestly don't know.
Yeah, sure. So this guy's tricky. We leveled off. When we see a graph where we do this and level off, what's it mean? For anybody. This is for anybody.
Which is equilibrium.
We're at equilibrium. What do equilibriums do if we start messing with stuff in the equation?
They shift to the direction where it favors.
Right. They shift to minimize what we do. So if I inject some CO2, what's the equilibrium going to do with that CO2 I inject?
It's going to decrease the amount made in the equilibrium.
Exactly. Right. It's going to get us back to what this value is, because remember, all right, the equilibrium is only affected by temperature, right? Like the overall equilibrium value, which is what's going on here. All right, so you want to say for C, right, it would be equal to 1.04. The equilibrium would shift to eliminate the CO2. All right, and then letter D says, is there enough data present to be able to determine Kp for the decomp of CaCO3? All right, so Angel, if we want to get a K value, in this case a Kp, how do we usually get K values?
By doing an ice table.
By doing an ice table, right? So we would look at our equation, right, which was it's right there, sorry. CaCO3 solid plus the CaO solid going to CO2 gas. All right, so if I were to write a K expression for this, right, what would you write in it?
CO2.
Okay.
And that would be it.
That would be it. Why?
Because the other molecules or solids.
Good. So all I need to get the Kp is what?
CO2's pressure.
Do we know CO2's pressure?
Yeah.
Yeah, absolutely. It's all over the place, right? It's in the graph. They told us it was 1.04 a couple times. So we absolutely have enough. So you guys just want to say, since Kp equals PCO2, we can find Kp because we have the pressure of CO2. Questions on that guy? Okay. All right. On to number 5. All right. So number 5, they give us a list of formulas, CF4 and F3O2. It says some binary compounds that form between fluorine and various nonmetals. All right. And are listed in the table above. A student examines the data and poses the following hypothesis. Right. The number of F atoms that will bond to a nonmetal is 8 minus the valence electrons of the nonmetal. All right, so it's saying, based on the student's hypothesis, what should be the formula of the compound between chlorine and fluorine, right? And the student's hypothesis says, all right, that it's the number of F atoms that connects, whatever this is, will be 8 minus the valence electrons in the nonmetal. All right, so Camille, what are you thinking on how to figure out what the ClF's formula is going to be?
So it would be 8 minus Cl's 7 electrons, so it would just be ClF.
There it is, right? That's what that was saying. It's 8 minus the valence electrons, right? And chlorine has 7 valence electrons, so Camille's right on the money, right? ClF is going to be its formula. And that's the pattern they're showing, right? 8 minus sulfur, 6, is why it's F2. 8 minus phosphorus is 5, is F3. 8 minus silicon's 4 is that. That was what was going on there. So in B, it says, in an attempt to verify, the student researches the fluoride compounds of other halogens and finds ClF3. In the box below, draw, all right, the dot model of the ClF3. All right, so Carmen, what is it they want us to do?
They want us to draw the the electron dot diagram.
Exactly, right? Talk me through it.
So Cl is going to be in the middle, and then there's going to be 3 Fs coming off of it.
Okay.
And then you have to do the electron bank. So Cl gives you 7, and F gives you 3 more 7s. And then you have to subtract 6 for the bonds that are already there. So you get 22.
Good.
And then you put the dots on the outside first.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18.
And then you put 2 on the Cl. Well, 4 on the Cl.
20, 21, 22. Okay, good stuff. So that's what's going on in letter B. All right, we get ourselves that picture. Into C, C says 2 possible geometric shapes for ClF3 are trigonal planar and T-shaped. Student does some research and learns that the molecule has a dipole moment. Which of the 2 shapes is consistent with the fact that ClF molecule has a dipole moment, justified in terms of polarity and structure? All right, so Elena, talk to me about how are we going to figure out if it's trig planar or T-shaped first?
You have to get the record for it.
All right, what do you think this guy's record is?
5-2.
5-2. What's 5-2's name?
That I cannot answer.
All right, that's why I'm saying you guys want to have that out in case they ask questions on it. 5-2 is T-shaped. All right, so we know it's T-shaped. Now, they want to know, will it have a dipole moment? Because we're expecting it to have a dipole moment. So dipole moment is code talk for what, Ethan?
It has a a different pull.
Yeah,
right?
uneven pool.
Yeah, that's what it
hole,
is.
dots on the center. So generally, what's our first check?
Dots in the center.
Does it have dots on the center?
Yes.
Yes, it does. Now, when we went through this chapter, we had 2 exceptions to our dots on the center rule. We had 2 records that had dots, but were still not polar. All right. Anybody remember one of them?
Was it 6-1?
Close. 6.
6-2?
6-2 can be an exception. It's square planar. All right. So this isn't 6-2, so it's not that exception. All right. And there's another one. 5-3. And I would probably jot those down on your little cheat sheet for that. 6-2 and 5-3 are your exceptions. They can be non-polar even though they have dots, right? And the reason is 6-2 goes square planar. So it looks like this. So there's this guy in the middle, and you've got an electron pair above and below. Well, the electron pairs cancel each other out, and as long as 1, 2, 3, your 4 corners are the same, then overall it cancels out. 5-3 does the same thing, right? 5-3 means 3 unshared pairs. So they go like this. Here's my middle guy. The 3 unshared pairs go around it, and then you get a bond going up and a bond going down. So the unshared pairs in 5-3 can cancel, and as long as this and this are the same, then it would be nonpolar. But this is neither of those records. All right, so you wouldn't have to get into all that. I was just reviewing to help you guys out. All right, so you would say the T-shape is consistent with a dipole moment because of the unshared pairs of electrons leads to bond dipoles not canceling, right? So whenever you want to say polar, you want to say bond dipoles don't cancel. When you want to say non-polar, you say bond dipoles cancel. So like even pool, bond dipoles cancel. Uneven pool, bond dipoles do not cancel, right? So you would say T-shape with its unshared pair has bond dipoles that do not cancel. All right, questions on C? All right. In an attempt to resolve the existence of the ClF3, a molecule with the hypothesis stated above, the student researches that compounds that form between halogens and fluoride and assembles the lips. So we got F gets F2. Cl, we don't know. Br gets BRF, BRF3, BRF5. I gets IF, IF3, IF5, IF7. And it's saying, based on the concepts of the structure, all right, propose a modification, all right, that tells you why they do this. So the first thing I would do, even though they don't ask it, is I would spot the pattern and see what we think should happen with Cl. All right, so John, if we were filling in this box here for Cl, right, what compounds would you make formula-wise? Yep. Did we lose John? Oh, no, John's still there. John, you still there? All right, we'll come back to you. Mia, if you had to predict formula, what formulas would you predict based on the pattern you're seeing?
So like a Cl2, maybe?
Well, remember, you're connecting this guy to F every time.
So ClF or FCl or whatever that one be.
Okay.
And then a ClF3.
Uh-huh. Okay, and why does that pattern fit?
Because it seems like all of them have the like formula with ones and then a 3, and then it goes to a 5 the next one, so it's like going in an order.
Exactly, right? So it was like, oh, what connected to F? 1F. So the first one had 1F connect. The second one had an F1 and 3 Fs connect. That's why Mia said these. Then we got F1, F3, F5, right? And you guys are seeing the pattern, right? All the way up to F7. So I like the pattern recognition. So if you look at the periodic table, all right, talk to me, all right, Sid, about structure. What seems to be happening as we go like this down the table?
The number of formulas you can have for each one is increasing with each one.
All right, and what is changing about these guys as we hopscotch down the table?
The number of orbitals they have.
Exactly, right? So F has 2 energy levels. Cl gets 3. Br gets 4. I gets 5, right? So to put this in terms of structure and periodicity, right? They just want you to talk about the electronic structure. All right, so Sid told us what happened. All right, write this down. As the number of energy levels increases, the number of fluorines that can attach increases in odd numbers. So as the number of energy levels increases, the number of fluorines that can attach increases by odd numbers. Questions on that guy? All right, so friendly reminder. All right, Angèle, I don't know why this is going to yours. I was definitely the first person in the meeting, but do me a favor and send me the video from the Google Drive.